get a good feeling, yeah. Get a feeling that I never had before. No, no, I get a good feeling, yeah. Oh, sometimes I get a good feeling, yeah. Get a feeling that I never had before. No, no, I get a good feeling, yeah. Just wanna tell you right now, I really do believe it. Just wanna tell
Check, check, check. 1, 2. What?
They are even. Bowls just fuck it up.
No, because look at the top right. Check 1, 2, 1, 1, 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1.
We could do 2 gobos on the outside screen.
One, two, 1, 2. Ha ha, 1, 2.
Je n'ai pas le temps de perdre la tête pour nous sauver de nous-mêmes.
Devnexus ever. So thank you for coming. We have folks from how many different countries this year?
Like
15, 20, 30?
120 countries.
120 countries, something around that. So anyways, thanks for coming.
There are some people here from Japan, which is very cool.
Yeah, and lots of people from Europe and everywhere, basically. So this is, Devnexus is probably now the largest Java conference in the United States or North America. Not planet Earth yet, but we'll get there next year, so we'll see.
Outside of Java 1.
Outside of Java 1. So how many people are from Atlanta here? Just a quick show of hands. Okay, so we typically have about 75% of the folks are from the ATL. So if you're here, please come and check out the Atlanta Java User Group. It's one of the biggest jugs in the world, and we meet every month on the
third Tuesday of the month.
Third Tuesday of the month.
Whatever date that is. Sometimes it's like the 15th or it's the 22nd or whatever.
So please come to the jug. We meet in Perimeter right by the Sandy Springs MARTA station. And we meet every month, so please come check it out. And we're always looking for people to help out with the Atlanta jug. So if you have some time or if you have some ambition to come and help us organize the Atlanta jug or Devnexus, please come see us. We'd love to have your help. If you want to speak at the Atlanta jug or if you want to speak at Devnexus, a good on-ramp to that is come speak at Atlanta jug and then get a little bit of practice in front of a friendly audience, and then you can step up onto the big stage here at Devnexus when it rolls around in February.
Most of the speakers you'll see here next 2 days, they started out speaking at a Java user group or a small meetup, and they've just progressed, and now a lot of them speak globally for a living. So it's a great place to start.
So, and we also just deployed a new website for Atlanta Jug, so we're taking it to the next level, as they say. Okay. So if you're looking for a printed schedule, we don't waste paper at this conference, so go to schedule.devnexus.com. It's a PWA app, and PWAs are the future, I think, right? So you don't have to install an application now to get a nice...
no more App Store, thank God.
Yeah. We don't have to worry for hours about like making sure that Apple approves our app and all that.
Burn an extra night,
right? So
call them.
So anyways, schedule.devnexus.com is where you can find a nice formatted schedule on your phone to see when everything is happening. And this evening we have the the No Pointers playing at 6 o'clock, so please stay. We have free food and most importantly free booze, and we'll have some live music from the No Pointers 2.0. That's today at 6 after the last session ends. So please come check that out and hang out with us. And who wants to drive home in traffic anyways, right? So hang out with us, and then you can go home leisurely after traffic finishes at 7:30 or 8 o'clock.
Drink responsibly.
Yes, drink responsibly. Also, if there are people standing in the back, you can go over to A412. We have a simulcast running for this same keynote, so if you don't find a seat, go into the other room.
Or you could take one of the hundreds of seats that I can see.
Exactly.
Front or the side or whatever.
So, and for the folks who've been to Devnexus before, you know that we do a big raffle. I think this year we're giving away a Tesla, and what else? I don't remember.
One of those SpaceX things?
Yeah, something like that. Maybe, yeah. So anyways, please stay for the raffle at the very end, and we have speakers, great speakers speaking all the way up to just before the raffle, so come and enjoy the speakers, enjoy the sessions, and stay for the raffle. Let's put it like this. It's better odds than winning the Powerball. Right? I can guarantee you that, okay? So
everyone is entered. If you're here, you're entered in the raffle.
Yes, but you must be present to win. And you can't, last year we had a fella who, his entire team went home and he had like 16 badges on. And we're like, no, that's not gonna work. I don't think that you can represent 16 people, so you have to be in person to win, okay? And we'd like to thank our speakers, our volunteers, and our sponsors for helping to make this event possible. We have loads of great sponsors who help us put on a great event, so please go see them in the atrium level downstairs. They're giving away free t-shirts, and they may also be giving away a free Tesla. I don't know. I haven't been to see them yet, okay? So our DevLounge sponsor is Lightbend, so you can go visit them. And I think the JFrog folks have like a coffee machine downstairs, so the sponsors have put a lot of effort into coming here, giving away swag, and go talk to them and see what they have to say. And with that, I would like to turn it over to Diane and Sean after a brief video. So, Bravo, play the video. Yes. All right.
Hot? Hot? How you doing? Hot? Are we hot? No. There we are. We're hot. All right. You're all hot right there. All right, so that Tesla thing, that's real. They're going to actually raffle off a Tesla, but the problem is it's the Tesla that's in orbit right now going to Mars. And so if you win, it is yours. You just got to go get it. So good luck with that, all right? So first of all, thank you, Vince and Pratik, all the volunteers, everybody that made this happen. This is the best conference I've been to all week. And it's just, I'm really, really proud to be here. And Diane's really excited. And we've got some cool stuff we want to show you. But first, we wanted to thank you for being here, all right? So before we get any deeper into this, yeah, we have a kind of a space theme because we do some space work. We work for a company called AI Solutions. We're an industry partner in the space industry. And we do contract work for NASA, NOAA, the US Air Force, various commercial agencies. We handle launch services, we design the missions, we fly the missions, we decommission the missions. So if it's space, it's usually us. We're involved. However, that being said, we don't work directly for NASA. We do the work for NASA. So our views do not represent NASA. We are not representing NASA right now. We are representing the research and the work that we are doing. So with that out of the way, Diane, would you like to introduce yourself?
Yeah, I'm Diane Davis. I'm an astrodynamicist. I work at NASA Johnson Space Center, and I'm designing the orbit that the Deep Space Gateway is going to go fly to.
What's the Deep Space Gateway?
Well, I'll get to that in a minute. Why don't you
Okay,
introduce
all right.
yourself first?
It's pretty cool, actually. It's space, so I like it.
It is space.
Some
I
of
like
the folks in
space
here
too.
might care. So what do? I am a software engineer. My specialty is data visualization, and at the moment, lately, JavaFX. Ooh, okay. Maybe I have to drive it, huh? Switch to the duplicate?
Yeah.
Okay.
There we go.
All right, great. So one of the things that we do to avoid humiliation is we, instead of doing a live demonstration of actual software tools, we're going to do a video. But at the prodding of some of the managers of this conference, they said, well, it's a dev conference. You need to show code. Okay? So what we're going to do, because it's a keynote, it's not a technical deep dive, we're going to show some bits of code at key locations that do some of the magic. We're not going to show you all the secret sauce because then I won't have a job. But you're going to get a little taste of it. And if there's not going to be any Q&A because of the format. So if you have any questions or you want to extend the conversation and discussion into a more deeper dive, either the code or the aerospace aspects, come see us afterwards, okay?
All right, we ready?
I think we're ready.
Let's begin. So I've spent the last 3 years or so working on the trajectory for the Deep Space Gateway. So the Gateway is going to be the next human outpost in space. And just as of last Monday, it got a new name, and it's now a formal project with NASA, which is very exciting. So
it means money.
Yeah,
They're actually going to fund it versus not.
Yeah, that's exciting.
Yeah.
So it's going to be humanity's proving ground for deep space technology. It's going to be our next outpost in space. So what this means is that we'll be able to test out our technology in deep space, but before we're too far gone. We're only 5 days away from home. And it'll also be a staging orbit for missions beyond the Earth-Moon system into Mars and asteroids and further beyond.
Yep.
So for more information, we've got the link here. But the important bit is that we need to find an orbit. We're headed out to the moon, but we need an orbit that's not too expensive to get into and to get out of from a fuel perspective, because we're going to be sending people and spacecraft there. And then from there, we're going to be launching into other parts of the solar system. Now, what we're used to seeing are low lunar orbits. Apollo went to one like this. It takes about 2 hours to go around the moon. And it's about 100 kilometers from the surface. The South Koreans are going to be sending a robotic mission into an orbit similar to this in a couple of years. But we're not going to go to one of those because it's deep inside the gravity well of the moon, and it's very expensive to get into that orbit, and it's expensive to get out. Instead, we're looking at a near rectilinear halo orbit, which is this big green guy here. It takes a whole week to go around. It gets about 70,000 kilometers from the moon. Now, that's nice because it's inexpensive to get into this orbit, and you can stay in it pretty inexpensively, and then you can get out of it. But when you get that far away from the Earth, you can see it's not an ellipse anymore. It's not a circle. So the pull of the Earth is very strong on this orbit, and also the sun. And as soon as you have more than one gravity field acting on your spacecraft orbit, it gets really tricky to design these trajectories.
But there's some advantages.
There are.
You want to go to deep space.
Yeah, so for example, we can do a maneuver to get out of this orbit, to go off to Mars, off to an asteroid, or even just dispose of trash that we're creating once we're occupying the spacecraft. But how do we find the orbit that we want? When we have multiple gravity fields, there's challenges here. There's an enormous data space. It's highly sensitive, so a tiny little change at your start is going to affect your trajectory enormously at the end. There's no analytical solution anymore to these orbits because we've got multiple gravity fields. And so it requires innovative design methods. How do we find the needle in the haystack? How do we find the initial state that's going to get us where it is that we want to go?
Yeah, I like hearing about, like, people talk about big data. That's cute. Your data is really big compared to that, right? So how do you do it? You do it with tools. And that's why you're all here. All the developers here. I'm not talking to the managers in here. I don't even know why you're here. So the developers, we make tools, right? We're builders and we're creators. And we're all about the code, right? And we've got this cutesy navigation screen, and we're hovering over each one in this video. We have all these sub-tools as part of this grander suite.
I make them do lots of work.
Yeah. We have all these tools, and that's great, right? But I want you to know that you are more than the lines of code that you write. You're more. It's not about the tools. It's about the ideas. And I hope that's the thing I want you to take away from all of this, is that you can make tools like this. We chose to do it with space, and you can too. But before we get started building tools, we have to know how to show the data. So why don't you explain that?
So we would say there's a lot of data. This is a big data problem, and we can't look at all the orbits simultaneously. So here you see a blue orbit. It's going around Jupiter's moon, Europa. And you can see the blue trajectory. And you can imagine if you had 10 trajectories there, it would just look like a bowl of spaghetti. So what we're going to do is just look at the green points. So every time you make a close approach to Europa, it's called a periapsis. And we're marking those green points there. So what we can do is get rid of the blue trajectory that makes that spaghetti and only keep the points. And you can see how those points in that periodic orbit form a pattern. And that pattern tells us something about the orbits it's created. So you can see there's 4 orbits here. And you can see the periapsis points, those points of closest approach, marked in white. And the patterns tell us many of the characteristics of the trajectory. So we can throw away the spaghetti, we can get rid of the orbits themselves, and just keep the periapsis points.
So what happens when we do that in mass? And this is only 845 trajectories, and it creates approximately 56,000 periapsis points. What if we take that information and we project it into a 2D plane? Okay? We make a map, a Poincaré map. It serves as a sort of analysis roadmap where we can find these ideal trajectories if we can find those points that we're looking for in this reduced but still dense sea of seemingly psychedelic chaos, okay? So the trick really is, now that we've reduced the data space, how do we interact with the data? How do we make the data the interface?
How do we make that map?
We do it with tools,
Yeah.
okay? And for this tool, we'll use 100% JavaFX. It is badass. And I hope you all, if you haven't used it yet, you look into it. Here we have JavaFX 3D. We decided that rather than force the user to parameterize all of their information and force them the right code, we gave them an interface which gives them instant feedback of what you see is what you get in 3D type of data editor. Okay, so what you have here is an Earth-Moon scenario. And you see on the left, if you can see it, we're adjusting some range sliders. What it's doing is it's expanding the min and the max bounds of where you want the spacecraft to potentially start from.
So these are all the initial conditions, the initial states. We're going to start a spacecraft trajectory at each of these points, and then we're going to propagate it forward.
Yeah, absolutely. And so what that causes is a psychedelic Borg, okay, which then is going to go attack the Earth, okay? Actually, the moon or one of the libration points. And so what are you seeing right now? You're seeing a scatterplot mesh that you can get for free, open source, from fxyz3d.org. I paid for the domain. Please start using it. But there are over 33,000 independent points being rendered in 3D and animated through space. Okay?
And then I'm moving them back and forth to attack the moon and the Earth with the Borg.
Have fun doing that in JavaScript.
It's good stuff.
Okay? Enjoy it. I don't even think you do it in Unity. Maybe, if you're really good. Okay, so great. So we got this what you see is what you get thing. And then we combine a 3D subscene with a 2D pane, which has some more traditional GUI controls, give the user a chance to export the data, and then boom, it immediately starts integrating from each one of those initial conditions, these trajectories that start flying around. But because they're all in slightly different altered states, they all go to different locations. And as the points are being captured, we collect them here. Now this, if we let this run, it's going to produce a lot of data. And so we're going to pause the video, okay? We're going to look at some code. All right? No live coding. Yeah, I'm a coward. So we're going to show some blocks of code. And I'm not going to show you great code. I'm not going to show you the right way to do this. I'm going to show you the way that I figured out how to do this and figured it out very quickly because I picked the right ecosystem to do the job. Okay? And if you want to talk more about maybe you know a better way to do it from the code I'm going to show you, come and see me afterwards. Okay? Okay. So what you just saw was that cube of initial conditions being fed into a parallel stream framework. Okay? When I say framework, I'm just using parallel streams. In fact, I'd be shocked if there was somebody in this room who hasn't used the streaming API at this point, or at least hasn't like strongly considered it. And I'm just doing those things in parallel. But there's some tricks you got to do. You have to make sure that your executions are embarrassingly parallel. That's not the same as embarrassing. Okay? I mean, all your executions must be completely independent. Fortunately for me, and maybe unfortunately, the integrations that we do are not really well suited for a GPU algorithm. Okay? They're in very dense data, so it's data bound, it's compute bound. They're perfect for CPU executions, which is why the parallel stream API works so well. So what I do is I have some pre-computing type stuff. Here's the function that does it. I increase the font size. I hope the folks in the back and in the nosebleed seats can see it. But essentially what we're doing here is we generate a list of bins, for lack of a better term, which each bin is a class object that has all the information you need to do an integration. And then we just feed them into a parallel stream. We do a PhD thesis in math, which I, to this day, haven't figured out, but this is her, right? This means something, right?
Yeah, absolutely.
Okay, okay, good. All right. See? See? Huh?
Don't get me started on start explaining this one.
It means a lot. But eventually, when it comes right down to it, after you've done a lot of math to be prepared, they get fed in parallel as the cores become available. This works great, by the way, when you're running off of a cloud instance, which has 52 cores or 72 cores. Or if you want to farm each one of these out and break it up into more cores, it works fantastic. It's still the same code. When this all comes down, what this all comes down to is this guy right here, and I really can't show you the secret sauce underneath because there's a lot of boring math, but there's also some tricky tricks that kind of it's the secret sauce. But essentially out pops 1,000 or 2,000 states where the spacecraft, I'm going to be here over this time, right? So in those states are points that we collect, and then we render those, okay? And so when we render them, it goes onto that canvas, okay? And I'm going to show you an example of the canvas a little bit later. So let's get back to the video, okay? We have to be a little sensitive to time. Okay. So great. We created a tool which lets the user generate the data that they want to work with. So now they can finally generate or work with the data, right?
So now I've got my maps.
Yep.
And they're beautiful. So this is a map that represents planar orbits around the moon in the Earth-Moon system. All right. So every one of these little points is a periapsis point belonging to a trajectory, and the colors represent the trajectory in the order that they were generated. So you can see that I clicked on one of the islands, and it creates this periodic trajectory that I never knew existed, but it's my favorite at this point. So
what you just saw is this like crosshair that I call the targeting reticule, because I like to come up with fancy names for the boring stuff that I do every day. And what you also might have seen a white dot jumping around. It's a cruise control for point selection. Essentially what it's doing is it's finding the nearest data point in data space, okay, by doing essentially a binary search in the various axes, okay? And there's a little bit more secret sauce. It's not quite that simple, but it's mostly that. And so in having these tools, we can immediately find these hard-to-reach points going from pixel space on the screen directly into the data space.
There's so much data on screen that even though it's all planar, so you're seeing all of the data at once, you can't necessarily see the islands that are hiding within it. But by doing a query on the data, we have a list of parameters that are interesting to me about the orbit: semi-major axis, eccentricity, inclination, a whole variety of them. And we can move those sliders, and it filters the data instantly so that I can see what's left. Right.
And then, of course, you do all this clicking and all this filtering, and you find something that you think matches your mission parameters. What does it look like? What is the real deal? What's my spacecraft going to do? Is it going to the parking lot on Mars, apparently, right? Where Tesla's going. Oh, a little fast, right? Let's go back a little bit. So, again, because we picked the right frameworks, in the same tool, we just add that trajectory we just found and re-render it in 3D. Okay?
And it's so interesting. So these are all around the Earth moon. They're all planar orbits. They're all at the same energy level, but look how different they are. They look nothing alike.
Yeah.
So these tools are fantastic because prior to something like this, you could use numerical methods to find these. You'd throw in a bunch of numbers, and you'd let your computer churn, and it would spit out a bunch of numbers, and you'd search through those numbers and try to figure out where your interesting orbits are. But what Sean's tool and what our collaboration has let us do is we can use the data itself, the visualization, to find the orbits. So we're incorporating the visualization into the design process itself, which is pretty
It's a big step. I mean, you know what they were doing before, and actually a lot of them are still doing because it technically works, is they're using BAS, big-ass spreadsheets. And they're just like, well, there it is, and then they sort, and they're like, oh, that's the one I want. It's like, well, how do you know? It's just
okay, so these are all planar orbits anyway, but we don't fly.
I want to show some code here.
You're showing code.
Yep,
Okay,
just a little bit. Okay, so let's back up. Reel it in. So let's go back to this real quick. There's a couple points to make here. This is a canvas, a JavaFX canvas, okay? Now, I know some folks in here have used it. I know some folks have used canvas-type objects in other languages. And some folks are like, I'm not a painter. What the hell is a canvas? Okay, so a canvas is essentially a memory-backed image that you can write directly to, okay? It is not event-managed, and I'm not doing it justice, but the way I see it as a developer is it doesn't care what you do with it. It's not going to tell you any events. It's not going to give you any nice-to-haves or any positioning. What you draw is what you get, okay? However, it's fast. It is fast. Like Geo Metro, Corvette fast, Dodge Viper fast, okay? And so I'm able to render, in this particular use case, there's, if you can see it in the upper hand right, there's 445 different data points being transformed onto the screen and rendered.
445,000.
Oh, yeah, I'm sorry. I add some zeros to that. Yeah. So again, have fun with that, JavaScript. Yeah, we actually looked at JavaScript. It didn't work. So we went with JavaFX. Now, you might be saying, so what? It's just an image, right? But the so what is that we're using these range sliders, which are from Controls.fx, just modified with some CSS, so thank you guys for your commits. Every time one of those minimum or maximum thumbs moves, every millisecond, it's redrawing that canvas dynamically. Because it needs to then cross-reference all that data to determine who's actually visible now at that point and who's not, based on the current constraints. That's how fast this is. So let's take a look at the code. Ooh. Oh, hey, this is NetBeans 8.2. Really great IDE. And I just want you all to know that NetBeans 9.0, the beta, Apache beta, has just been released. So go get it, guys and gals. OK, so where is my paragraphs? There you go. OK, so at first glance, you might think, oh, this is complicated. It's actually very simple. The beauty of using canvas-type renderings is that it's, as long as you do your pre-processing ahead of time so that you're not blocking the rendering thread, you're pretty much good to go. So walking down through this top block here, I'm getting the insights of my window area. What I want to do is figure out how big my current screen is. What if they resize the screen? What if they shifted it on screen? I then set my canvas to those bounds. I clear all the data and all the special effects that I've added up until then. And then I get into the juice of it all here, right here. Okay? It's just a stream where I filter based on a variety of parameters. Okay? Well, is this dot in view because of the data space? Is the trajectory that it's part of, is that in view? Is it part of a group that's been hidden? Blah, blah, blah. And what all it boils down to is we go through each one of those stages of filtration until we get down to the no-nonsense, here is the data that we're going to do. And then we determine what color it is. We do a color lookup. So we have different color schemes. We have manual, psychedelic, jet, if you use MATLAB. Boy, that's a MATLAB joke. Nobody here got that.
I got it.
That was brutal. You didn't even laugh, though. You let me die out here. Oh, God. They're not going to invite me back. OK, so once you know your color, then you need to take your data. And here's a little bit of secret sauce I'll share with you. Mostly because if you look hard enough, these are patterns that you can find online. You need to transform your data to your pixel space, OK? Your screen space, right? Because guess what? Your screen is not the same as your data. Our data goes generally between -1 and 1. Well, you have more pixels than that. So how is that done, okay? It's doing a transformation on the fly each time. And here is an example right there. Now, I know there's ways to be faster. Why not transform it ahead of time and only do the transformation when the screen changes? Could do that. I'm already rendering at 500,000 points with no hiccups. I don't know why I have to go to that level of trouble. But here is the formula, okay? So if you want to do something crazy like that, you just do this, okay? This isn't really the secret sauce. I'm not going to show you the secret sauce. I keep telling you I'm not going to show you the secret sauce. Okay, let's go back to the video.
All right, so what we've looked at here are orbits that are in plane in the space. But as we all learned, the enemy's gate is down. There's 3 dimensions in space, and we don't generally work in the planar world. So our orbits in general are multidimensional. So we have a map like this, and this is really a cloud. So this is a periapsis map that's a cloud in space, and we've smashed it down into, we're projecting it into 2D space. All right, so you can see I've just clicked on 3 orbits. Here's our bowl of spaghetti that I keep referring to. And so this is where this visual query becomes really powerful, because hiding in this particular map is a kind of orbit, and I'm pretty sure this orbit hadn't been found before, but we found it using these maps. We're calling it TULIP. It's a 6-to-1 resonant orbit, and it flies close to the south pole of the moon, and it has apolloon up at the top. So you can get really close images down here, and you can hover and linger in the top. So you can find these orbits in these 2D maps by filtering out the data.
Almost like an MRI.
Like an MRI.
Yeah, right. Yeah. But okay, so we found it in 2D, but we don't know. Now we're almost at a disadvantage now, because we found it and we know how to find it, but we actually don't know if it's what we want, because we need to get into this highly inclined elliptic orbit.
So why stay in 2D, really? So let's drag the map out of plane.
Yeah. So now we're back in the JavaFX 3D. It's the same map with the same filtration. Now we're under in 3D, and oh, look at this interesting structure. It's like some weird space Pokemon. It's like with little pink legs and
there are my islands. I promised you they're under the South Pole. So now you can see, there they are, under the South Pole. Those are my periodic orbits underneath there that we can find. So we're going to look at the data, but these are just points in space, and we've got 6-dimensional trajectories. We've got 3 position coordinates and 3 velocity coordinates, and we only have 3 on here. So let's add some. So we're going to replace these points.
That's right, yeah. So what we're doing is we're taking a scatter plot, and now we're adapting the triangle mesh rendering algorithm to also take into account direction as a 4th, 5th, and 6th parameter. So now we're visualizing 6 coordinates in space. So now you can see not only where the spacecraft is, but where's it going. And that's a big deal, I'm told at least. I don't care, but I mean, you know.
And we don't have to stay in Cartesian space, right? We've got other parameters that we're interested in. So what we've done is allowed you to change the coordinates that you're plotting this in. So we just put eccentricity there on the z-axis instead of z position, and you end up with like a.
What is that?
It's like a halo laser sword thing.
What's halo? What is halo? I don't know what halo is.
It's a plasma sword. That's the word I wanted.
Okay.
It's just like one.
All right, so great. So let's go back a little bit of code, right? Let's go back to this nerd weapon that you talk about, and let's spin it so we get it's a nice bright thing. There, bam. Okay, right. So how do we? This looked different when we first started, and in the video somebody clicked around and changed the parameter space, and it automatically replotted the whole thing. And by the way, it's doing this in 3D, and there's tens of thousands. I forget, what is the total number of points in this one?
Something like 10,000 or?
No, it's based on one of the original. I think it's like 30, but whatever.
Maybe 30.
The point is, we're rendering that stuff like this, like butter. Okay, so how do we make it like butter? So the scatterplot mesh code is freely available at fxyz3d.org. Okay, I keep hammering that because I had a little something to do with that. But this is a hot-rodded version. Okay. And so I can't give you the secret sauce for the hot rod part, but you can get 90% of it from fxyz. But let's take a look at how the data gets modeled. It's actually quite simple. We don't have time to go through the whole thing. So what I decided was I would show you the code. How do we figure out what the visible points are and where they're positioned in space, in screen space? Because again, you have your data. You need to transform it from your data space to your screen coordinate system, okay? So here it is. We get what points are visible at any moment, okay? And what we have to do, the trick here is you have to figure out what your minimum and maximum bounds are for your data so that you can scale it and normalize it within your screen space. So there's a little bit of wrangling here where you have to figure out what the total mins and maxes are so you can calculate the ranges. That's in this first block here, okay? Again, this is not This is not the secret sauce. This is how you do it, or one way to do it. And then once you have that list of nodes, you need to go through and transform each one of your nodes to your screen space. And so essentially, in 3D, this is the formula that it looks like. I have a little check there because if something is absolute 0, it causes real issues. So we have to be able to, if there's like a very tiny range, it's an epsilon thing. But essentially, we're transforming our coordinates there, okay? And so, and one gotcha, JavaFX, the y-axis translates in normal Cartesian space. You ever done? Remember doing this in math? Math, the different left-hand, right-hand coordinate systems.
In my world, Z is up.
Nobody? You're all remedial math people? Well, you are at Devnexus, so bunch of dummies. Okay, so essentially, the y-axis in the math world, it becomes the z-axis in the JavaFX 3D world. And also, if it's in 2D space, y is actually 0 at the top going down, which is flipped, sort of, from most scientific and mathematic standards. But in the 3D world, y is 0 at the center, because the origin is at the center of your scene. Just little gotchas. Just keep that in mind. You have to keep these little things into account. OK, that's really it. I overdid it.
No, you're good.
I always overdo it.
OK,
let's go back to the video.
OK.
How are we doing on time?
I don't know.
I don't have my phone. Hey, how are we doing on time?
It's 9:46.
OK. We have about 20 minutes. OK, great. So we should get through this. OK, so
all right, so we plotted all these orbits, but now we want to look at them, because I keep promising you they're 3D orbits. So these are these tulip-shaped orbits that we're so excited about. There's 3 of them plotted on top of each other, and you can see that they're periodic. But we're not actually going to one of these. We're going to go to a halo orbit. So you might ask, what is a halo orbit? They're periodic orbits in the Earth-Moon frame, and they're called halos because if you were standing on the moon, it looks like they make a halo around the Earth. Okay, so in the Earth-Moon rotating frame, they're periodic. And we can get into these. We've flown missions, actually, already. Genesis, ACE-WIN, and SOHO, and Artemis have flown to orbits like this. So we can design, for example, trajectories using this tool in between the tulip and the halo. We've shown those in talks in the past, but we're going to focus really on the NRHO and how we get into and out of it in this talk.
That's right. So, OK, so we know what we want. We know where we want to go. OK, how do we get there? All right. There's no phone app yet. Talk to Gluon. We're working on it. But you make tools, OK? So we've made this tool similar to the other one with the what you see is what you get editor. But in this case, there's some complex convergence, like optimization. It's not optimization, but similar to that type of algorithm to compute these things. So what we do is we give the user the tool not to just make a libration orbit, a halo, any libration orbit, any type of libration orbit in any system in the solar system. That's what people like you do. You don't make things pop out. You don't compute numbers. You make things that make it easy and beautiful to do. So keep doing it.
So what we have here is the first member of each of these different periodic families that exist in the Earth-Moon system. And then we take this initial orbit, and we can use a process of continuation to build from that orbit and make like halos that are on the wall here. And so
that's right.
Yeah. So what we do is we're gonna save this properties file and then use the continuation to create the family. So this is the southern family of the L2 NRHO. So the gateway is planned to go into one of these guys. All right, but there's actually 4 NRHO families. There's northern and southern. They're symmetric across the Earth-Moon plane. And then the L2 side is away from Earth. The L1 side is in between the Earth and the Moon. And you have halo families in each of these spots.
Yeah, you know what's happening, and I don't know if we have enough time to show the code for this bit, but when each time they dragged those property files in, the configuration files that have all the parameters in them, it's actually calculating the optimal, the converged halo family trajectory, and then rendering it, integrating and then rendering on screen on the fly. That's how fast it is. That's not sped up. Those aren't pre-calculated.
They're correcting. It's taking an initial state, it's correcting it into a periodic orbit,
yeah,
and then moving on to the next family member. So then you get this family, and we can interact with the family on the screen as a whole. And so what we're going to do is we're selecting one of our halo orbits.
From a grid view from Controls FX, thank you.
And then we're going to design some maneuvers off of it. So if we already know like approximately the magnitude of the maneuver that we want to perform, we just maybe don't know where around the orbit to put it. So we're going to put a maneuver in the velocity direction at lots of points, 20 different points around the halo orbit. And we're going to propagate it forward to see where they go. All all right?
And so the red and the blue families are from the exact same initial conditions around the halo, but one is going in the velocity direction, i.e. I'm going in this direction, I'm going to apply a delta V. And then the anti-velocity direction is I'm going in this direction, but I'm going to apply the mirror opposite.
A retrograde burn.
A retrograde, yeah. And it creates dramatically different results. But what if you don't know what your narrow band is? What if you need to take a step back and say, oh, I don't even know where to begin, I just know what I got? You need a bigger tool. You need Monte Carlo type capabilities. Again, that's the perfect use case for visualization. So we've created this other tool called a batch transfers tool.
So we've got here 3 billion potential departures. So we've got departures all the way around the halo orbit. We've got departures in any direction and any magnitude of delta V, and we can run them all at once to find the trajectories that we're looking for, all right? And so out of this, we can create a map of periapsis points, or we can render the trajectories themselves. So we're going to limit the design space to relevant ranges so we don't plot 3 million orbits on the screen.
Yeah, I mean, JavaFX is great, but I mean, there's limits even to this.
It's really the PC that starts to complain when you try to plot 3 million trajectories.
In case you haven't noticed, I like JavaFX. I keep pumping it, you know, because it made it so I can do this. So I'm not trying to pitch the product. I love it because it enabled me to get to this quicker.
So we're going to configure the data output, and then we can run this locally or on the cloud. If I'm plotting a bunch of trajectories, but I'm only plotting 104 of them. So if we have large transfers, it's one of the reasons this tool was one of the reasons we got into looking at the cloud for some of the computations.
Man, look at that thing. Yeah. What's it look like?
Yeah, look.
That's actually a bug. I need to make an icon drag over, but I'll get to that.
Yeah. All right, so now we have all these trajectories that have departed from the NRHO, and they go in lots of different places, all right? So you got some that are headed over to the Earth, over here, right? In that little star-shaped thing looking on the Earth. You've got some that are headed out into heliocentric space. So let's say we want to get out of the NRHO and go to heliocentric space, all right? But we've computed this just in the Earth-Moon equations of motion, but once you get out of the NRHO, suddenly you're in a Sun-Earth-Moon system, and the sun starts pulling. If you have the sun in the right orientation, you can actually get the sun to pull you out of that orbit. So for a tiny little delta V, you can get out way into heliocentric space.
That's good. I know that one. That's good. We want to get away. We
do.
want to go far away. I don't care where, just far.
So what we've done is recompute. So what we've done is we've got a switch there. So Sean will let me change equations of motion. So with changing the equations that we're propagating forward to generate these trajectories, and you can see how they're different, all right? So they're just a little bit different. The sun's pulling on them differently. But the green ones have the sun. The orange ones don't have the sun. And so you can really assess the effects of the sun on these trajectories. Yeah.
So let's take one more opportunity to show a little code, because we're almost done. And I don't have a clock in front of me, so I'm kind of brainballing the timing here. But one last chance before we get to the last bit. Let's go back to that part where we're doing the batch transfers, and we're calculating a bunch of conditions and then integrating, and then we're rendering at the same time, and it's not really blocking anything, and everything's just kind of flowing. And so how is that done? Okay, well, back to NetBeans. Okay, so it's using a a classic computer science technique, just producer-consumer threading. Okay, there are some gotchas. So when you're doing producer and you've seen your hello worlds for producers and consumers stuff. I'm not going to go into detail about that. I'm just saying we use that. But some of the gotchas are that you need to generate your data you need to set up all your data ahead of time. Okay. So if you're going to do this with JavaFX, you'd use a task. There's an object dedicated to this type of thing where you define your work. So here's my consumer task. Okay. And all I'm going to do is, depending on what settings are on the board at any moment, I'm going to take whatever's already been integrated, and we have a queue, a concurrent queue. We add those, the integrated trajectories to that, and then it just, every 10 or 15 milliseconds or so, it kind of pops off whatever's in the queue and then plots it. Okay? Now sometimes you got to play with that timing a little bit, and I'm sure there's better ways to do it. I found that the best way to get the quickest performance without starving the CPU computations is to put just some basic sleeping patterns in there. Real short, just a few milliseconds. Okay, so once you have your producer thread, you can define your consumer thread. Okay, so the producer thread, I just defined the consumer thread. This is the producer thread. Okay, and what this one's doing is actually doing the integration. So all it's doing is it's going through. Remember that parallel stream pattern? Yeah, I'm not very good at writing new code. A lot of copy paste, a lot. It's bad. It's bad. And so there it is. And then, interestingly enough, we go into our little secret sauce that does our little mathematical integration, and out pops a whole bunch of trajectory states. And once they're done, we push those onto the concurrent queue for the consumer thread. Then, ta-da, we just start our threads, our tasks. That's it. This isn't rocket science, right? I mean,
It is a little.
I think we kind of agreed not to do that joke, but then, whatever. I've died up here so many times, I'm like a lich. I'm just going to keep like joking. Ah. Okay, that's it. Let's finish the video so these guys can get out of here.
I think people want to get to their talks at 10.
Yeah. Well, we started late. I don't think it's our fault.
No.
Okay, Pratik. Okay, so.
Okay, so what orbit did we find? All right, so we did all that work to find an orbit that leaves the NRHO and goes where we want it to go. So here's our halo orbit. So this is similar to what the gateway might be headed to. It's a 9-2 lunar synodic resonance, which means it's a pattern.
It's juicy.
It is.
It's juicy.
And so we've departed from paraloon because its trajectory is by far the most sensitive at paraloon. So we put a small maneuver at paraloon. We leave immediately from the NRHO. The sun starts yoinking on the orbit. You can see we do a flyby the Earth before we head out into heliocentric space.
And that's the end game. We're going to spiral out, and we're going to go somewhere. And the where is up to you. It's not up to me. I just make the graphics. So over the next 20 years, this is what it's going to look like. All right? Now, normally I would ask, are there any questions? But I can't do that. I would like to have a shout out to the people on the team, us, and a couple others. But I'd like to take a moment. We come to these developers conferences, and we're so excited. We're amped up. I mean, look how excited she is. We get, settle down, all right? Just settle down. But we get overly focused on the code, okay? The lines of code. We measure ourselves. I'm seeing this disturbing trend where people are measuring themselves by their lines of code, and that's good. We need code, right? I'm not saying don't stop coding, but you're more than the lines of code that you write, all right? It's about ideas, okay? We need all the code we can get. But we also need good ideas, ideas that make this world better, all right? Ideas that make you better, ideas that inspire the guy next to you to be better, inspire the girl on the other side of you who commits code in the middle of the night, generously, anonymously, better. Ideas that lift people up. We need all the lifting we can get. Don't leave here with the latest API, and don't leave here with the latest framework. Leave here with an idea. Meet somebody, get an idea, and make it happen. You get one chance on this earth. Well, I guess maybe this implies you could do it somewhere else too. Okay, so you get 2 chances in a couple years, but you get one chance on this earth to make something good and to make this world better. And you can do it, and we need all the help we can get. Thank you.